right, hi everybody. I hope you can hear me okay and that this is somewhat presentable. Fingers crossed. Yeah, we're going to talk about Gauss's law for magnetic fields. There's not much to it, but we're going to talk about it because it's all going to combine, and then we'll get into light and stuff. Sorry. Then we're going to get into Faraday's law, which is what I'm going to end you with. And then we'll get into light next time. Okay, all right. Just to remind you what we did for Gauss's law for electric fields, right? We had a charge inside. It was a positive charge, and that emits some electric field, right? And then we could make some imaginary shape. They make some weird kind of sphere here and weird shape, enclosed shape. Again, it's got to be an enclosed shape, and there's some electric field that goes with the area vector, right? And it's the dot product of the electric field with that area vector that gives you what we call the electric flux. And so if we add up all of that electric flux around, that's the integral of the electric field dotted with dA, and then Q is the charge inside, and then epsilon naught is a constant. Yeah, that's called the permittivity of free space. Again, that's essentially how easily an electric field will move through empty space. Okay. You guys did the derivation, so here's my solution right here. Basically, the electric field, if we make it a sphere for a point charge, is constant. We pull it out. We integrate from with respect to A from 0 to A, and basically you get the area of a sphere. Again, this is not a sphere, but that's what we did before. Area of a sphere is 4 pi r squared, and then you isolate E, and you get the electric field equation, where again, this is Coulomb's constant. Okay, you could do the same thing for an electric charge. And then basically the flux here, though, is going to be negative because the electric field goes into negative charges, right? So the electric field is going this way. Area vector tends to point out of the whatever shape you have, right? So if you got a sphere, the area vector kind of radiates out of the sphere by default. It's just a convention. And then so the electric field in this case would be negative. Okay. Or sorry, the electric flux would be negative, right? The electric flux will be negative. So yes, this would be negative, negative. Okay, and then so I give you a bit of a problem. Well, what if we had a charge over here? So here is a charge, a positively charged bar, right? And let's say it's emitting a constant electric field. We would probably need another bar to do that, but just to not complicate it. It's emitting a constant electric field through this enclosed space. So I make up some shape, right? So I make up some shape, maybe like this. Maybe it's like a little rectangle right here like this, and I put it here, right? And then I got some electric field going in and some electric field going out. So again, convention with the area is that the area just radiates out of every single spot. So here at the perpendicular, it's pointing up. Here it's pointing this way. Here it's pointing that way. The area vector is, but the electric field is all going this way, right? And so it's a constant electric field. So I'm going to pause because I want to know, what is the flux going to be? What's the flux going to be? Is the flux going to be positive or is it going to be negative, right? So here, well, yeah, so pause the video, try that for yourself. So see if you can do that. Okay, hopefully you unpause the video. And so here's the solution. Well, if the area vector is going to be constant, right? All those little area vectors are going to be constant because we've got the same kind of area, the same surface for each side, right? So the same area. So the size of the area vector is the same. And the electric field is constant for this. It's all pointing to the right. Except here, the flux is going to be negative because the electric field is pointing opposite the direction of the area vector. So here the flux is going to be negative, where over here it's pointing in the same direction as the area vector. So the flux is going to be positive, But if the values are the same, when you add them up, they're just going to cancel out. So you get zero flux. And basically, if you have a charge that's not inside, that hopefully makes sense, because again, Gauss's law is essentially that the electric flux is equal to the charge inside divided by epsilon naught. Well, if there is no charge inside, it's not going to generate any flux. So yeah, that's the idea. Okay, so let's move right along. Well, what about if we have a magnet? So that we see in a magnet, right? You got a north pole and a south pole, always with a magnet. What about the flux that it generates? So, okay, we can, so I got a magnet like this. And so, again, the flux here is going to be, well, truly it's the integral. So it's the integral of the magnetic field dotted with dA. Like that. That's the magnetic flux. Yeah. So we did the electric flux. This is the magnetic flux, B dot dA. And so, yeah. Well, what about the flux here? Well, I can make a flux here. So I'll start here. What about the flux going through here? I've made a shape like this, right? Similar to this thing right here. And basically, I can see, so again, the area vectors would point out this way and this way. And here I can see the magnetic flux going in and then the area vector going opposite direction. Here it's going to have negative flux going in, but then it's going to have positive flux going out. And the flux will add up to give you 0. What about over here? So again, you've got magnetic field flux going in and then also coming out. So again, that's going to add up to 0. Again, you try to make shapes so that the magnetic field is constant throughout to make it add up easier, but it really doesn't matter what shape you make. It's just the math's going to be more difficult for you if you make a wackier shape, or if you make like, yeah. So what about here? Well, the area, the flux is also going to be 0. Or I've got this shape here. Here you've got some flux going to the left here, or you got some field going to the left. Here you've got some field going to the right, and such that they all add up again to give you 0. So what does that mean? Basically, Gauss's law for magnets is that the flux, the magnetic field dotted with the area of any magnetic field is always 0. And basically, the idea here is the kind of big idea that's gotten from this is that there are no magnetic monopoles in nature. There's no magnetic monopoles. In other words, there's always a north and a south pole, right? There's no just north pole that radiates out a magnetic field like there is a positive charge that radiates out electric field. So we saw this in honors physics last time, where we basically said, well, what if I keep breaking a magnet and breaking a magnet? And even at the electron, the subatomic level, right, even if as you keep breaking the magnet, you always have one north pole and one south pole. Again, there is electric monopoles. There are electric monopoles, like positive and negative charges, and that's why that the flux is equal to some constant, right? But here, there are no magnetic monopoles, so the flux in this case is equal to 0. So this is Gauss's law, with that. So so like this, having just a north pole that radiates out magnetic field, that does not happen in nature. No. Okay. There you go. So next up, and this is getting to the idea of... you know what? I'll just use a PhET simulation with this just to kind of give you a reminder of that. So Faraday PhET. Sure, what the heck? So I think that ain't helping. Let's see, there we go. So here you got a magnet. The magnet generates some field, right? And And basically, if you take that magnet and you change the magnetic field, or in other words, the magnetic flux, in some way, you can even flip it. Or can I flip it? Does it allow me to flip it? I haven't used this one in a while. Yeah, that basically you can generate but basically I generated a current. So you can see as I move the magnet in and out of the loop, right? The electrons move, and that generates for me a current, right? And that's what lights the light bulb up. So by doing this, I can generate basically the idea is that a changing magnetic field will generate an electric field. That's an electric field that pushes the electrons around. So let's go then back here like this. So let me rewrite this really quickly. In honors physics, we wrote it like this. We said basically, we did talk about magnetic flux. So we just said though, because again, honors, everything has to be constant, right? So we said if you change the magnetic flux, that means change the magnetic field, change the area, or change the angle between those two. That basically the rate at which you do that, that's why we got divided by time, will generate an electric field, or basically a voltage. So again, we use E for voltage here. I don't know essentially why it's called EMF is what it's called, electromotive force. But so yeah, generally when it's generated by a magnetic field, we call it an EMF. But it's essentially a voltage. Yeah, so that idea, using more of our calculus stuff that we've been using here, is essentially that a voltage is created, and again, I'll just say EMF. So like that. And that's caused by a changing magnetic flux. So here's like the simple version that you can do that with. And I've got those absolute values right there. And so yeah, this is the rate of change of magnetic flux with respect to time. So again, remember the flux is just you add up all of that magnetic field dotted with area. Okay, and so we didn't get into this. This is a bit of me throwing something in there, but just because from what I'm going to show you, I'm going to add this in there. Basically, honors physics, we did this a little bit, but again, this is getting really kind of fancy. So basically, a voltage ends up equaling the integral of the electric field dot dl. So it's basically if you go a certain distance along an electric field, that'll produce a voltage. Essentially, if you go down, right, you can go down in voltage or you can go up in voltage, and that means basically you're going to go with the electric field or against the electric field. Again, I understand if I haven't really explained that well, but basically you got this then, and this whole idea here is called Faraday's law. Faraday's law. So basically, this is a voltage, but it's a fancier way to write voltage. It's the integral of the electric field dotted with the path that you go, and that's equal to the voltage that gets produced. That's equal to the magnetic flux, the rate of change of magnetic flux, ddt. And then basically. So yes, this is Faraday's law, and Faraday figured this out. He figured out, oh look, when I move a magnet inside this coil, I'm producing a voltage. I'm producing a current. Yes, and it turns out that was almost true, very close. So there's this other thing called Lenz's law, where Lenz says, yeah, that does happen magnitude-wise. However, if you want the actual direction, there's a negative sign in there. So, and that's where I got oops, because Lenz's law says, oh, there's got to be a negative sign in there. That basically, whatever the rate of change of magnetic field, the electric field that gets produced moves in such a way that it produces its own magnetic field that goes against the change in magnetic field. So if the change in, not magnetic field, magnetic flux. So if the magnetic flux gets bigger, the voltage that gets produced, or the current that gets produced, produces its own current. Sorry, the voltage that gets produced produces its own current that creates a magnetic field that opposes that change. So if the change is positive, it'll create a negative magnetic flux. If the change in flux is negative, it'll create a positive magnetic flux. So I got an example here really quickly. I tend to say instead of flux, I say magnetic field, but truly I mean flux. So you can imagine if I have a small magnetic field and it goes to a big magnetic field, right, the change in flux then points this way, or the change in magnetic field points this way. That's the change in B. And so what's going to happen is the current that gets produced is going to create a magnetic field that goes against the flux, against the change in flux. So if the change in flux goes up, then that means then the magnetic field produced by the current must point down. And so if you had a loop, like this, right, doing this, so the magnetic field, again, if you remember your right hand rule, the thumb is the direction of the current, finger is the direction of the magnetic field. So the magnetic field is pointing down, and my thumb points like this, such that the current is going to go and flow around like that, like I have in this thing here. So what I'm going to do then is in my classroom, you'll see a device, the little ring device that I demonstrated for you guys. And I want you to try and explain how that works. So that's it. You're going to give me a claim evidence reasoning. How does that work? How does the ring pop off like that? All right, bye.